plugging in answer questions in the first one. The center adoption of the orthogonal, so from I can do that, right? So I just plugged in plug in the values of integers, right? Give negative as well as plug in the values. Yeah, I got 0. So I got the answer. Plug in. That's not. That's the second part. That's 30.
These are all B values.
You have to plug in everything.
Solving for all B that satisfy those two.
I already found. I need to watch. Yesterday was too early, so they made me reserve, or they made me like treat like references. You know, they said reserve information's open at like 7 a.m.
And when did you do it?
The day like yesterday, I did it like
What day was that?
Because I need a day where I can't do it after school. I had to do it last month. Like the more I have out the break. What was I gonna find? It's the same format. Very great day. Oh, freak is this? What is that? What is this? Yeah, we're going. CCN. Oh, like this. Good. I don't even know what that was. It's good.
It's going to be not where.
So you oh, D? Like what?
I didn't know we had 11 of the answer. So did we find most of it?
Dart is the would be like a combination. Anyway. I'll check that resolution. See if I got a spot. Only money for like. Yeah. These logins are all. How long is the exam? What's preferred? No, I think it's like 75. I think it's okay. It tastes like this. Sugarland. Why do you should so like we're right. 2 billion of them dropped. Still have a big. That's fine. Dude, I mean, they sound like that yesterday.
I'm thinking
Yeah.
one of the.
Oh, wait, I'm confirmed.
Oh, that's not bad.
Your schedule, your start time is Tuesday, right? Is it seems to be? Wait,
We have one thing.
I don't, yeah.
there's like confirmation. You can have it right after the last.
Say, I can stay later.
Here's right. It's not even that fun. Like a little first.
No, you get here like 30 minutes.
I
just, check first my over next.
Oh, you know how fast I'm on this. I am never late.
When
I'll
I
have to
start.
get my.
Sure.
Okay. Good morning. So, any questions before we get started? One thing I want to remind everybody is that, you should already reserve your spot for the midterm one, okay? If you haven't done so, please do that as soon as possible, okay? And this week, we are going to finish chapter 12. Next week, we are going to work on the more questions reviewing the content of chapter 12. Okay, so everybody can download the Hangout on Teams. Okay, so I will encourage you to do the question yourself first, if possible. Okay, because they will allow you to come to this lecture room, then know what to expect, right? And then you can really clearly see the way you solve problems, how is actually the same or different from mine. Okay. I know some of you go to this tutoring sections, which will solve the problem in all different kind of ways. Okay. I would strongly encourage you to actually follow the way I solve problems. This makes you be happy. Because after many years, I feel that's like the most straightforward way to get you to the answer the soonest. Okay, and every time I come to my office hour, then I was still doing the same thing, so it's actually consistent. Okay, so the logic should be actually very simple and clear. Okay. And this is CHEM1312. I could say that this is CHEM1312. Anything that involves too much changes of concept, it's not going to be helpful for you, right? It should be straightforward. So, with that being said, okay, any other questions that you want me to address? Okay, so I think after we change the office hour, there are actually more students. They come to the office hour, which is actually a great sign. Okay, so I want to remember that you spend a lot of money for these courses. So make it count. Okay, get what you want. It's very important. Yeah. So one thing I tell my students is that life is actually a marathon. I think everybody knows that very often. Okay. So unless actually only living things you can do, then actually let it go, you can achieve. Okay. To really achieve your goal, you want to actually be efficient. So you need to have a very clear goal for what we want to do and have a reasonable plan. Okay, so for these courses, the plan is actually get the grade that you want. Okay, and then fully use the resource that you can have. Okay, I provide a lot of resource for these courses, and I hope you actually found it really useful. Okay. All right, so if let's actually no questions. The things we're going to do today is actually very simple. Okay, we're going to get back to this Arrhenius equation. Okay, so equation I mentioned in the previous lecture, we have actually finished the very last two last two questions in the hangout. So I'm going to finish that first today. And after that, this is actually the plan for this week. So basically, those are the contents for chapter 12. Okay, so we're going to talk about 2 points of chapter 12 today, okay, which I highlighted on the board already, right? So the first point is actually called the chemical quotient and equilibrium constant. Okay, so I think everybody know what equilibrium constant already. That's the things that you learn in high school. Okay, but we want to actually emphasize the differences between the chemical quotient and equilibrium constant. Okay, and the other main point we're going to go through today is if I give you a chemical reaction, I give you a equilibrium constant. Okay, so if I do a massage of my chemical equation, for example, I put in the equations, or I multiply a coefficient to my equation, that will actually affect your equilibrium constant numbers. Okay, so how to actually calculate those numbers? We're going to teach you today too. Okay, and on Thursday, we're going to enter the most important part of chapter 12. Let us actually feel the most confused. Okay, which is actually we're going to introduce the famous concept, the ice table. Okay, has everybody heard of ice table before? Okay, some of you are nodding your head, but some of you don't. Okay, so ice table stands for initial, change, and equilibrium. Okay, so this is actually a concept you need to get very familiar with for chapter 12. Okay, so every time we do an experiment, okay, when you do your CHEM1312 experiment, so it's have to mix your reactant, right? So when you mix the reactant, the ultimate goal is actually get your product. Okay, so you start from a given condition. Okay, is that condition at equilibrium? You just throw all the reactant into your beakers, right? You allow the reactant to react. Okay, and they will react. Okay, so under this basic setup, would you say your system is at equilibrium? It is not. Okay, it's very important that you recognize that. Okay, so what is actually the equilibrium we're talking about is that after all the reaction is completed, okay, then we say the system reached an equilibrium. Okay, so you need to recognize when you read the questions, okay, you need to recognize, okay, the number that provide the question, which stage do they belong? Do they belong to the initial stage? Or other question actually describe the change of the reaction? Or let's say describe the status at equilibrium. Okay, that is actually the most important part that you need to be familiar with, so you can actually really handle all the questions in chapter 12. Okay, let me emphasize this again. For chapter 12, the goal is that you can recognize the information within a question. Okay, once you see the description, you need to start to think about which stage the question is actually describing. Is that actually initial, change, or at equilibrium? Okay, if you can do this well, your chapter 12 is actually very simple. Okay, but most of students actually get very confused about these descriptions, which we're going to tell you how to keywords they're actually looking for. So you can actually 100% sure the information is actually for the I, or C, or E. Okay, so that is actually the most important conceptual things that you need to comprehend after this week's lecture. All right. And then once you know that the very last topic for chapter 12 is actually the very famous Le Chatelet principle. Okay, and the idea is also very simple. Okay. So what it describes actually once your system reaches equilibrium, if you change the equilibrium, okay, you add more reactant, you add more product, you increase temperature, you lower the pressure. Can you predict how the reaction is going to move to the reactant side or move to the product side? Okay, so that is actually a very interesting concept afterwards. But if you actually can understand what equilibrium means, how this process evolves, then it will be actually a very simple conceptual questions as well. All right, so those are the things we're going to go through this week. Any questions? Okay, so now then let's actually finish chapter 11 first. Okay, so the very last one we talk about is the Arrhenius equation. Okay, so I think right now everybody should actually have a good idea we talk about the reaction kinetics, right? So every time we talk about reaction kinetics, the figures that you should be able to draw out yourself is this energy versus reaction coordinate plot. Okay, so we start from the reactant, we end with the product, right? And depending on the end of the reactant product, it can either be an endothermic or exothermic reaction. So we draw these things previously, right? So the energy is actually y-axis, x energy is actually your reaction coordinate. That line is actually pretty important. That line will definitely show up in your meter 100%. So you better know how to treat all of it. You should know every single things I list over there, reactant, product. Okay, you need to know what is actually exothermic, what's endothermic. Okay, you need to know how many intermediates, depending on turbine draw, how many transition states, how do you define the EA, right? So those are the basic terms that you should know, right? So you should always remember the reference is always your reactant, right? So the energy difference between your reactant and product. So this give you the delta H, right? The peak to your reactant give you the activation energy, right? And the shape of the curve will define how many transition states, how many intermediate that you have, right? So number of this is the number of intermediate, right? Number of peaks represent number of transition states. Okay, so those pretty much the things that you need to know. Okay, so what we're going to talk about today is actually this EA is actually the energy barrier that your reaction need to overcome, so that you can actually convert a reaction to the product. Right? So apparently, how do you actually overcome the activation energy? So how? When you do reactions, what do? You put things together, and then what do? You mix it and then you heat it. Okay. Why do you heat it? So what does heating mean? Have you ever think about that? Heating is actually providing your molecule enough energy. Why do they actually provide energy? Because to overcome the barrier, that's actually the way to provide energy to your reactor. You heat it. Okay, so once you heat it, you got more energy. Everybody can understand that concept? Okay, so it's very simple. You heat it, molecule get energy. Okay, so once the energy is higher than your EA, then you hop over that energy barrier, then you convert into your product. Okay, so that is actually a basic idea. So this actually tells you that the EA, the molecule that can actually hop over the activation energy barrier, okay, well, depending on the temperature that you provide. Okay, higher the temperature, you have more higher energy molecule, higher energy reactant. Therefore, you have a chance to actually get more product afterwards. Okay, so this is actually a very easy, intuitive connection between the EA and the activation energy. Okay, so if you go back and look at the equation, okay, it tells you the reaction rate will relate to two parts. One is called the frequency factor, the capital A. The other one is actually EA and the T, right? You can see on the top is actually EA, at the bottom is actually T. Okay, so EA and T is actually kind of like tied together. It describes the populations of molecules that have higher energy than your EA. Okay, so this whole E terms, the exponential terms, is describing that concept. Okay, so what does A means? A is so-called the frequency factor, right? What frequency? Collision frequency. Okay, so for reactant A and B, they can actually produce product. They first need to actually combine with each other, right? So every time you put things in a given space, they're going to be used around. But from time to time, there's a chance to collide with the charge, right? So the chance that collides with charge will be defined by the frequency factor. Okay, of course, there's actually a mathematical way to calculate that. Okay, right now, of course, it's the okay, and you don't have to know the details. The thing is not actually conceptually how this thing was formed, right? It's actually first you actually encounter. Then you look at what they encountered energy to overcome the barrier. It does, then you have a reaction to happen, right? The larger the number means actually you have larger the rate constant. Okay, so I hope I actually give you a better sense, the physical sense about this equation. Okay, so these two equations I draw here is just actually the same. The only difference is actually I take the natural log on both sides of the top equation. So that if you rearrange this, that's the equation you're going to get. And you either memorize one or the other, it doesn't really matter. Okay. The interesting is that since we know at different temperatures, you are going to have different rate constants. Okay. So you can actually first write out this equation using different K and T, right? You can write out natural log K1 equals to natural log A minus EA over T1. You can also write out the same equation, but you say it's actually K2 and T2. Okay, so you have two equations. And if you're dividing these two equations, it comes to this equation that you want to memorize. Natural log K1 over K2 is going to be equal to EA over R, parentheses 1 over T2 minus 1 over T1. Okay, so those are the equations that can tell you, yes, this is actually equation contains 5 variables. K1, T1, K2, T2, and the EA. Okay, so the question I'm going to encounter is actually if a question mentioned about two rate constants. Okay, two temperatures, then you know from those information you'll be able to calculate your EA. Right? Other type of question will be you want that. You actually provide 4 out of 5. So you have 5 parameters, right? You can actually provide 4 parameters and ask for the remaining one. Okay, but the equation wise, it's the same equation to use. Right. So everything is equation provides 2 different temperatures. Okay, about EA, and you know this lecture goes to equation. Okay, this is the only equation contains 2 equilibrium, 2 rate constants and 2 temperatures. All right. So those are the things that we want to know. Okay. So then we can actually go back to very last 2 questions. Okay, so let's look at this. So it says a first order reaction have an activation energy of 48 kilojoule per mole and a frequency factor of 5 times 10 to the 10th per second. Calculate the rate constant at 27 degrees C. Right, so what is the keyword here? So that's not keyword. It is sort of another the one I want to see. No? No? Frequency factor, you can consider yes. Okay. Yes. Every time you see this activation energy, there are only 2 equations. Okay, K equals A times exponential minus E over T. That's 1, right? The other is actually natural log K1 over K2 equals to E over 1 of T2 minus 1 of T1. Only 2 equations. Every time you see activation energy, there are only 2 equations that you can use. Okay? Therefore, you know. Okay, our QD pad, right? What's the things we want to actually calculate? Rate constant K, right? If you read the question again, then identify the things you want to solve. You should be able to know the things you want to actually calculate is very constant K. So what are the data? What are the things that we know? EA equals to 48. Kilojoule means this, right? So you get an EA, and then you get what? Frequency factor, which is your capital A, right? Which is going to equals to 5 times 10 to the 10th power per second. Temperature, 27 degrees C, which is 300 K, right? So you add 273 to convert degrees C to K. Okay, so that's all the data that you have. And since you know the keyword is activation energy, right? And you know how the activation energy is actually related to your rate constant K, to this equation. Okay, so that will be your plan, right? So you know what equation to use. So after this, then you check what are the things that you have. Do you have EA? Yes, you do, right? Do you have temperature? You do. Do you have the frequency factor? You do, right? What are the things you are looking for? It's this guy, right? So all you do is actually to plug in all the numbers that you have. Exponential negative 48 times 10 to the third power divided by, what's the R you to use? How do you know it's actually 8.314? Yes, joules per mole, okay. But what is actually easier? How do you actually know when you need to use 0.0826? When to use 8.314? Every time you feed this term, pressure, you see the term pressure. For example, the vapor pressure, osmotic pressure. Okay, they all have the R, right? Because they have pressures, you have to use the R that content is ATM inside. Okay, activation energy doesn't have that feature. It's like a general term about a reaction. Specific describe the gas property. Therefore, R. All the time we use 8.314. Okay, so you can actually use that to help you understand which R that you should use. Okay, so here will be 8.314 times T is 300. The temperature is need to be in Kelvin. Okay. So once you have this, the next important and key thing is what? You need to know how to actually use your calculators to enter the names, right? So I would suggest everyone to bring out your calculators. Practice it. Okay. Make sure you can get the number. Okay. So right now, many of you should actually feel the importance of using calculator, right? Because once you come to my office hour, I will ask you to take out your calculator and push the button and get the number for me. Okay, which is a very essential part for you to get the grade that you want. All right. So if you enter this one is actually really simple, right? The only thing you need to be sure is that you should know how to actually enter this exponent term, how to actually enter this negative sign, right? So those are the things you need to actually practice. Okay, so if you do everything correct, then you should be able to get this K equals to 219. Okay, so these are the things you need to really practice. Okay, so let's recap how we solve this problem, right? First, read the question. Find out the keyword activation energy. There are only two equations that's associated with activation energy, right? And then you read more carefully, you start to see frequency factor 8. Okay, and you get your value of your EA, you get your temperature. Okay. Then now the equation for you is A equals A times exponential negative EA over RT. Okay. Then the next thing to do is actually just plug in all the numbers. Okay, and then make sure you actually upgrade your calculator properly. Then you'll be able to get the answer correctly. All right, so any question for this? Good. Okay, next question. So the first order reaction has a rate constant of 0.52 per second at 34.1 degrees C. If the activation energy is 63.6 kilojoules per mole, calculate the temperature in degrees C at which the rate constant is 0.979. What's the keyword? What's the keyword? Activation energy. Okay, activation energy is actually one of the most easily recognizable keywords. Every time you see activation energy, there are only two equations here. Okay. So once you know that it's actually activation energy type of questions, right? Then you want to ask you, what's your Q? What's your Q? What are the things we're looking for? Temperature, right? Okay, we're looking for temperature. What's the data that you have? So you have a rate constant, K equals to 0.52 per second at 34. The temperature equals to 34.1 degrees C, right? What else do you have? You know your EA is equals to 63.6 kilojoule, right? So times 10 to the third joules per mole. And then it actually provide you another rate constant, right? Equals to 0.979 per second. Okay. So everybody's fine with the things I wrote on the board? Can you roll the things on yourself? Okay, so once you write all this, what did you see? How many rate constant do you see? 2. Okay. So that's actually the second question we just mentioned. Natural law, K1 over K2, right? You have 2 rate constants. If you see 2 rate constants or 2 temperatures, that's the go-to equation. Okay? So then you have a plane. Right, so a plane is actually, you know, right? The older matters. Okay, it has to be K1 over K2. But this one is start from T2 minus 1 over T2 minus 1 over T1. Order matters. Okay, if you flip the order, you will never get the correct answer. Okay, so you have to really memorize the equation in the proper way. Okay. All right, so once you write this out, okay, you want to actually re-examine the data that you have. Okay, let's say this is actually the first rate constant, K1. Therefore, the temperature associated with it will be T1. Okay, this is actually a second rate constant you have. And then you'll realize that the things is actually asks you for this, right? If you read the question again. Calculate the temperature in degrees C at which the rate constant is that number. right? So let temperature is actually your T2. You are solving for T2, okay? So now you actually have everything. Then next thing you just plug in, right? Natural log K1 0.52 over K2 0.979. Going to equals to EA 63.6 times 10 to the third divided R 8.314 times 1 over T2. We don't know what the temperature is, right? Minus 1 over T1 is 34.1 degrees C, but into convert it to K, right? So you add 273, they give you a temperature of 307.1 K, right? So this will be 307.1. Okay. Then you can start to use your calculator, right? You can calculate this. You can calculate that. You can calculate this one too, right? So you can simplify your equation. Okay, so if you do the calculations, you should be able to get, make sure you actually do that because I want to spend some time on this. So you should be able to get this when you use your calculator. Okay. And then you divide this on both sides, right? So you divide 7.6497 times 10 to the third. 7.6497 times 10 to the third. Therefore, we can get a number of negative 8.2717 times 10 to the negative 5 equals to, this one will simply equals to 1, right? So you have 1 over T2 minus 3.2563 times 10 to the negative 3. Okay. Then you add the things on both sides. Therefore, you know your 1 over T2 is going to equals to 3.1736 times 10 to the negative third. Then you take the reciprocal of T2, which you take the reciprocal of this. Therefore, you can get your T2 is going to equals to 1 over 3.1736 times 10 to the negative third. That give you 315.1 K. Okay, but because you want to have degree C, therefore you minus 273, then you get a temperature equals to 42.1 degrees C. Okay. Everybody fine with this? Why do I do this? All this is like simple calculations, right? But why do I do this? Because I realized that many of you did not actually practice how to push a button enough. Okay. Will I be able to actually go through these things for every single question? The answer is actually no, right? This actually takes a long time for me to write. So it's not possible for me to go through every single step here. Okay, because I believe that as a student, undergraduate student, these calculations, you should be able to do it right? But that's actually something that is actually not very straightforward because we are not very good at handle the unknown in the denominator in general. Okay, so you can see I want to show you like how I actually break the things down step by step, right? So this is actually my unknown, right? So I want to actually keep that the same all the way to the very last step before I flip it. Okay, then all the other calculation I can actually handle it myself without much trouble. Okay, those are the things that you should actually practice a lot and become very good at, so that you can make sure you have enough time to do your midterms. Okay, so the number one thing I heard, okay, after midterm one, many students will come to me and tell me that, and Dr. Chen, I really understand every single thing you say in the lecture. Okay, I also understand the questions in the return, but I did poorly for midterm. Right, and I asked him like, what's the reason? Okay, and later I learned that for this calculation, you do it too slow. It takes forever for the student to actually figure out the answers, right? So these things can happen to the student, it can happen to many of my other students too. That's why I want to make sure that you know how to do this operation. I want you to practice these things as early as possible. Okay, if you don't practice now, that means you will need to practice in your midterm, right? Then the chance you're going to get a grade that you want will diminish. That's what I observe. Okay, so I cannot say you cannot do it. Okay, but if you that's the route you take. Okay, 99.99% of the time, what I saw is that you did poorly. Your midterm one, right? And these things will get even worse for the midterm two, because midterm two is the things that even more confusing to the student, and then calculation is even more complicated, right? So you need to really pick these things up right now. That's nothing say, okay, I will do it later for this. You need to do it and get master of it right now. All right, so I hope I emphasized enough. So every time you do your calculations, make sure you have your calculator with you. Make sure you enter the calculator properly. Okay. All right, so let's say for chapter 11. Okay, now we're going to enter into chapters that you sort of are more familiar with. Okay, equilibrium. Okay. So the first thing I want to introduce is this term called the chemical quotient, Q. Okay, so for a given chemical reaction, AA plus BB, like it is CC plus EB. Okay, so that's actually the equations, the chemical equations you're going to have. Okay, then you can define your chemical quotient Q as C to the 6th power times C to the D's power over A to the H power times B to the D's power. Okay. I want to ask you a few questions, okay, and try to participate as much as you can. We call A and B as what? Good. And C and D is our, okay, so if you look at chemical quotient Q, what's on your numerator? Products. What's in the denominator? Yes, this is the theory. The equilibrium, the chemical quotient Q is the ratio between the product and your reactant. And the notation we use is product over reactant. Okay, so let's say the first concept that you should have. Okay. The second question I want to ask you is that we use Q to represent our chemical quotient, right? If you look at that equation, is that equation the same or different with or from the equilibrium constant K that you learned in the past? Are they the same? Equation-wise, are they the same? Be confident, okay? Yes, they are the same. Okay, so why do we actually want to create this term called the chemical quotient Q? Why don't I call it equilibrium constant K? Why? Okay, so if you actually watch my YouTube video, okay, you should know that chemical quotient Q is a universal expression. Okay, no matter what the status of your reactions, you can write out your chemical quotient Q overlay it. Okay. Equilibrium, on the other hand, is a special case. Only your chemical reaction reached equilibrium, then you can actually write a number based on this equation. Okay, so every time we say the K, right, how do we call it? Equilibrium constant. A constant. It is a constant, right? Why it is a constant? Because at equilibrium for a given equation, the concentration of your reactant product, they are fixed. If only they reach that concentration, then we call it at equilibrium. Okay, so equilibrium is actually a special case. Okay, then you can only write out your equilibrium constant K using this specific equation. Okay, once your reactant and product they reach the equilibrium state. Okay, because the value is unique, therefore the K is unique and it will become a constant. Okay, so that's why K, you should actually see that now that K is very special. You can only write K when your system is at equilibrium. Okay. On the other hand, Q is anything else besides equilibrium. Okay, you can write Q at any given conditions. Okay, but when the system is at equilibrium, your Q will merge with your K. Okay, so that's the concept. Okay, everybody get a concept now? Okay, if you get a concept, then listen very carefully to my version now. Today I'm going to mix 3N of A, 2N of B, and I have 1N of C and 1N of D in my container. Then I let the reaction to happen. Okay, so I have this 3, 1, 1, 3 things going on. Okay. Then I want to write out the ratio of my product over reactant using that equation. The number I get will be what? The Q. Okay. Let me restate my question again. Okay. I have 3N of A, 1N of B, 1N of B, C, and 3N of D. Then I let the reaction to happen. Okay. So with the information that I provided, do I get Q or do I get K? Q. Yes, you are going to get Q, right? So how do you actually see B's concentration to product coefficient you have over AB product coefficient that you have, right? Product over reactant. So how do you know I'm going to get Q? What's the word I say? I say I let the reaction to happen, right? When I say I let the reaction to happen, do my system reach equilibrium already? It's not, right? So under what condition you will be able to allow to write K? When I say the system is at equilibrium, Okay, so the statement will be something like this. Okay. At equilibrium, I have A of concentration of 3N, B concentration of 1N, C concentration of 1N, D concentration of 3N. Okay, so remember, in this statement, I say at equilibrium, right? Then you know there's a time. You can use the equation to write out what? Your K. Everybody follow the things I say? This is actually the most important concept for this chapter. I want to make sure you can follow this. Okay. So the other way to describe it is actually if the question says A has a equilibrium concentration. Okay, every time this keyword equilibrium or at equilibrium, that's the only time you can write out your K. All others has to be your Q. Is that clear? Okay, so I hope by now you see the difference between Q and K. K is just a special case and only valid for your status at equilibrium. Okay, but equation-wise, they look exactly the same. Okay. The second important concept that you have is that when you let a reaction to happen, what is actually the destination? It's actually at equilibrium. Okay, so depending on your current status, okay, you can predict you are going to move to the product side or to the reaction side. Okay, so by now you should see it clearly. Q, you can consider that is actually your initial. K is when you reach equilibrium. Right? So we always start from here and end with equilibrium. Okay. Therefore, by compare your Q and K, then you should be able to predict how the reaction is going to move. Okay. So we say the chemical quotient, that specific equation is really the ratio between product over reactant, right? So if you compare your Q and K, so if Q is larger than K, what does it mean? Q larger than K means if you keep your reaction the same, right? You can consider your Q is the status you have more product than equilibrium. Because expression-wise, they are the same, right? It's always a ratio between product over reactant. If your Q is larger than K, that means in the current status, you have too much product, right? But your goal is actually go to equilibrium. Since you have more product than your equilibrium, that means the reaction needs to shift to the reactant side. So they have a chance to become equilibrium. Okay, that's why I write here when the Q is larger than K, then you want to move to the reactant side to lower down your product concentration. Therefore, you will look the same as the equilibrium. Okay, so that's the meaning of this. If your Q is lower than K, then it is just the opposite, right? You want to produce more product so that you can eventually become K. Okay, so under the case, you know your reaction is going to move to the product side. All right, so that is actually the first things that we need to learn. The other thing I want to talk about is that inside your these chapters, you are going to sometimes see these things KC, sometimes see KT. Every time you see this K, it means it's equilibrium. Okay. So the equilibrium constant P means actually if you express these things, if your reactant product they are in the gas form. Okay. So it's not going to using concentration to describe your equilibrium constant K. Rather, they're going to use the pressure. Okay, so the P stands for pressure. Okay. So if you use pressure to write out your equilibrium constant term, then we call it as Kp. Okay. If you use concentration to write out your K, that term is called Kc. And these two are interchangeable. Okay. And the equation to change it is that you use the ideal gas law. Okay. So that Kp can equal to Kc times RT delta N, where delta N was computed by the coefficient differences between your product and reactant. Okay, and here things we are going to calculate the pressure. See, the R now become the terms they contain ATM. Right? So use these values. Okay, so we'll give you examples on this. The second key concept we're going to learn today is that right now we learn how we can actually write out the equilibrium constant based on the given chemical reaction. If I change the way I write my chemical equations, your equilibrium constant will change accordingly. Okay. For example, if today I have a chemical equation in which it has an equilibrium constant K1. Okay. If today I flip the reaction orders, okay, so product become reactant. Okay, so you can see that in the equation you're going to write, you kind of shift the things, you flip your equations, right? So once you flip the chemical equations, then the new equilibrium constant will equal to the original one to the reciprocal, will be the reciprocal of the original equilibrium constant. So it is straightforward. Everybody understand what I say? If you flip the reactions, the equilibrium constant will be the reciprocal of the original values. Okay. Here, I guess right now, everybody know that so this is actually the equilibrium constant you're going to get for the first equation, right? The second one is you flip this reaction. Reactant become product, product become reactant. So the K is going to equals to, now this is actually your product, A to the A's power, B to the B's power, C to the C's power, D to the D's power, right? And then if you want to express the equilibrium constant of this guy using the original equilibrium constant, then you can see that this is equals to the reciprocal of that, right? I flip this equation upside down. Therefore, I know this should be K1's negative 1 power. Everybody fine with the things I just said? Okay. So now, the other thing is actually, if you further multiply a coefficient in front of the overall reaction, okay, then whatever coefficient you add will actually show up on the exponent of the new rate constant. Okay, so if you compare this one to the original equation, you can see that first you flip the reaction, second you multiply a coefficient n, therefore the new equilibrium constant will equal to the original equilibrium constant. You have this negative sign, right? Because you flip the reaction. You have this n because you multiply a coefficient n to the original equation. All right. So these are the things that you should know. The other one, the very last one is actually if you combine two equations in which the first equation has equilibrium constant K1, second equation have equilibrium constant K2. If you're adding up, the new equation is going to have a new equilibrium constant K3, which is going to equals to the product of K1 and K2. Okay, so those are the things that you need to actually memorize so that we can actually handle all the questions that we have. Any questions so far? If not, let's do some questions here. Okay, consider the gas phase reaction Cl2 plus Br2 that give you 2 BrCl, for which Kp is equal to 32 at 500 K. If the mixture is analyzed and found to contain 0.49 bar of CO2, 0.29 bar of Br2, and 2.1 bar of BrCl, describe the situation. Okay, so this question will ask you, what status am I? Am I at equilibrium or am I not at equilibrium? If I am not at equilibrium, then how the reaction direction will move to? Okay, so Q, right? I want to know Q K. If Q larger, equals, or smaller than K, right? These are only three possibilities. Which one is actually the one, right? And then I want to know the reaction direction, right? When will it, which direction will it move? Then you have your data. Okay. So you have equation Cl2 plus Br2 that give you 2 BrCl. Then it tells you the Kp, right? Kp means if I write out my equilibrium constant, it will be the pressure of my product, BrCl square over the pressure of my reactant, Cl2 first power, pressure of my Br2 first power, right? And this has a value of 32 at 500 K. Okay, so let's take the first data that you have. And then it right now tells you the pressure of my Cl2 is 0.49. Pressure of my Br2 is 0.29. And pressure of my BrCl is 2.1. Right? You don't know what status it is, right? But you know, you can just compute the equation, right? So you can assume it's not at equilibrium. Okay. I can compute my Q. The way you compare your Q is the same, right? Equation-wise, it's the same. So The pressure of your BrCl is actually 2.1 seconds power. The pressure of your Cl2 is 0.49 first power. Pressure of your Br2 is 0.29 first power. Okay. So once you compute this, you should be able to get a number of 30.95. Okay. So let us actually Q that you can compute based on the given function. Then you want to compare these two values, right? Are they the same? They are not the same. One is almost 31, the other one is 32, right? Which one is actually larger? The K is larger, right? It means at equilibrium, you should have more product, right? The K is what product over reactant, right? Since your K is larger, it's actually your K has more product than the current status, than the current given status. Because the current given status, you only have your Q of around 31, right? That means at the current status, you don't have enough product, right? So that you should write, since my Q is smaller than my K, okay, you don't have enough product, right? So you need to actually move to product side to produce more product so that you will eventually get to your destination, which is equilibrium. Okay, so these are actually the things that you should be able to write yourself. Okay, so the Q and K comparison, okay, is a very standard type of question that we encounter for chapter 12. Okay, so the main concept is you should know that the equilibrium is the destination. Everything you go to equilibrium in the end. Okay, yes. KT is equilibrium constant calculated using pressure. The P stands for pressure instead of using concentration. Okay, so in this case, you can see that it's all gas, right? So if your reactant product are all gas, the most common used unit will be either bar or ATM, doesn't really matter. Okay, but we write, that is just a notation, tells you the equilibrium constant was calculated using the pressure. Is that clear? Okay, any other questions for this? So if not, let's actually key take-home message. Okay, you should be able to, based on the value of Q and K, to predict how the reaction is going to move. Okay. Okay, second question. At a certain temperature, the Kp is 0.25 for the given reaction H2 plus Br2 give you 2 HBr. Calculate the value of Kp for the reaction HBr become half H2 plus half Br2. Okay, so this is actually a very standard type of questions. I give you the K for a given equation. I actually ask me the K of another equation. Okay, so this is actually the second point we mentioned in our hangout, right? So calculate the new equilibrium constant based on a given equilibrium constant. The way you look at it is that, okay, Q, we want to know the K new, right? The new equilibrium constant for a given equation. And the data that you have is, you have H2 plus Br2, that give you 2HBr. This one you have a K equals to 0.25. Okay? And you want to know if today I have an equation which is HBr equilibriate with half of the H2 plus half of the Br2. And then I want to know this, right? So the this is actually we want to look at and compare the given equation that they want you to solve. How is that related to the equation that has equilibrium constant? So if you look at these two equations, how are they related? Okay, let's flip, meaning the reactant become product become reactant, right? The second thing is actually you notice that coefficient-wise they are different. It divided by a factor of 2, right? So based on the rule that we tell you, the K new is going to equal the original K. All the things that change will actually show up in your exponent, right? So you write all those changes in the exponent. You flip, therefore you need to put a negative sign, right? So, and then you multiply what? You multiply 1/2, right? So you write 1/2 over there. And then you know your original K is 0.25. And you do this operation on your calculator. Okay, so if you do it right, you're going to get a value of 2. Okay, practice this on your calculators. Maybe you can get the value of 2. Okay, so that's actually the second question. Any question for this? Okay, if not, let's do one more. It's actually a little bit more complicated, but it's the same principle. Okay, so the Q is still the same. Okay, so given the value of K showing below, you have these two, right? So you have two equations with given equilibrium constant K1 and K2 of value 2 and 3. And you want to calculate the K for these equations. Okay, N2 plus 2O2 give you 2NO. Okay, so again, you still want to calculate your K new. Okay, the data that you have is two equations. N2 plus O2 give you 2NO, where the K1 equals 2. Second one is actually NO2 equilibrium with NO plus 1/2 of O2. You have equilibrium K2 of 3, right? And then you want to know if you have N2 plus 2O2 that give you 2NO. You want to know the K new, the value of that. Okay, so this is actually the setup that you have. Okay, the way you solve this type of question, okay, you want to look very carefully about the target equation. Okay, so that is your target equations, right? So now tell me, what are your reactants? What are your reactants? N2N, N2N O2 is your reactant. Okay, so you actually use that as a proof. Okay. In this type of questions, you are going to see multiple equations on the top. The goal is that you want to add those two equations up. Okay, that eventually give your target equation. before you add these two together, you can either flip the equation, you can multiply some coefficient to your equation. But the end goal is that give you the target equation that you want. Okay. So since right now you know who your reactants are, right? So the basic thing is actually you want to put the reactant on the reactant side. Okay. So if you look at first equation, it's N2 your reactant for the target equation. Yes, right? O2. Yes, right? NO2. No. Okay. So if the expected reactant in your target equation show up on the reactant side, that means you probably don't need to flip it. But if it is not, for example, in your second equation, your O2 is actually on the product side, right? That means you probably have to flip it. Okay? So once you flip it, then pay attention to the coefficient. For your target equation, the coefficient of your O2 is what? 2. Okay, that means after you flip your second equation, very likely you actually multiply a factor of 2 before you can add these two equations up. Okay, and if you do that operation, okay, I'm going to rewrite this one into, I'm going to flip it and multiply a factor of 2. Therefore, I get O2 plus 2NO then become 2NO2, right? So I flip and then I multiply a factor of 2, right? So once I do this operation, I have a new K2, right? Which will be the original K2. Since I flip it, I put the negative sign in the exponent. Since I multiply 2, I put negative 2. Right? So it will be 3 to the negative 2 power. Everybody fine with the things I just said? Okay. So once I do that, then I will need to actually add this guy and this guy together. Because once I adding up, I will realize that the N2 becomes the target N2. 102 plus 102 give me 202 in the target equations, right? 2NO is going to cancel out. And the product becomes the target product. Then I get back to my target equations, right? So the next thing we do is really just add, let's say this is equation 1, 2, 3. Okay, so I add 1 plus 3. Then I can get my N2 plus 2O2 plus 2NO. My new K will equals to K1 times my K2 new. Okay, and up to this point, you know your K1 is 2. Your K2 new will be 3 to the negative 2 power. Okay, then if you do your calculators, then you're going to get a value of 0.222. Okay, this is actually a very standard question of you encounter. Okay, but the goal is actually very simple. So starting from your target equation, recognize who your reactants are. Okay, and then go back to the given equation that with the rate constant, that equilibrium constants. Try to flip one fraction numbers of those equations before you add it up. Okay, so right after that, you add it up, we obtain your target equation. Then operation-wise, it's actually very simple. All the things you do will have influence the exponent of the equilibrium constant. Okay, so that's all for today. Thank you.